We're going to talk about a simple machine learning technique, KNN classification. So we have some observations that we've already classified, and the goal is to take an unclassified observation, something we don't know, and predict what classification would be best for that. This is a simple idea, and it's actually an extremely simple procedure. We look around at its neighbors and assume the new observation will be classified as the same way as the things around it. KNN is just simple notation for the kth nearest neighbor. We usually choose k to be an odd number because we'll be taking a vote of the nearest neighbors that were already classified, and an odd number avoids a tie vote. If I choose to look at 3 nearest neighbors and 2 out of 3 are classified in a particular way, then this procedure would predict the new observation should be the same. The art in it, and there is quite a bit of art here, comes from defining near. By what measure are we going to say that one observation is near to some other observation? It's a perfectly simple-minded machine learning technique to implement once the background is set up. But there's a lot of complexity about how to set up that background. What exactly is near? How near is near? Suppose we want to classify somebody as whether or not they're admitted to college. Typically, college admissions are going to have some weight on GPA, usually between 0 and 4. Admissions might also put some weight on SAT scores, which are, between 200 and 800. 800 is a little bit different from 4. Those are very different scales. If we constructed an index that just added the two numbers together, then you'd basically have a classification based on SAT score. Whether somebody got a 604 or 601 doesn't really make a big difference compared with somebody who got a 611 or 614. So, GPA would be completely swamped. So going back to our previous discussion about normalizing, this would be a case where an analyst might normalize both scores to be in the 0-1 interval. But is that enough? Are there other information relevant? That's where some of the artistry comes in. This is a good place to take a detour. Scaling problem is very similar to questions of ranking. And we see lots of rankings out there in the world, especially the popular press. Somebody produces a ranking about the top colleges in the US, or the best cities in the US, or the best athletes ever. A while ago, Sports Illustrated did a ranking of the best athletes of all time. Somehow managed to compare Babe Ruth with Serena Williams with Secretariat, the racehorse. Yeah, total clickbait. But, even comparing athletes within a sport, it's tough. They play different positions. Now, you might ask, does statistics give me any guidance on how rankings ought to be done? The answer is generally nope. Sorry. Sometimes it may feel like a lot of what I'm teaching you is actually things that you might have hoped to know, but actually don't. I apologize. But rankings are really difficult. If we have a simple distance measure of a one-dimensional variable, then we can manage a ranking. In sports can rank how many games did a team win. That's a number. Doesn't take fancy math to determine that 17 is a bigger number than 16 and rank them. What if they're tie games? Sorry, no good answer. Once you add in even one more number, you're looking at a two-dimensional graph, so you need to weight the two distances. With 3 numbers, 3 dimensions, all the wheels come off. There's some economic theory here. Ken Arrow, a CCNY alum, proved it is generically impossible to aggregate together people's utility functions. And a ranking of bundles is a sort of utility function. Thus, it's impossible generically to come up with any ranking that satisfies basic desired criteria that will accurately aggregate together the preferences of more than one person. You might hope there's some measure to do the rankings the right way, but the answer, nope, sorry, nothing. Generally impossible to do. Anyway, back to KNN machine learning. For example, in class, we'll look at adverse childhood experiences and mental health days. Whatever career you're considering in psychology, you should have some idea about the prevalence of different conditions, risk factors, and outcomes. So much human decision-making is based on an assessment of the likelihood of different risks. So here we'll do our usual work with the data, plus a little more. So the data tells us how many days of the last month from 0 to 30 where the person said their mental health was not good. We will lump that into a few groups. 0, 1 day, up to 5 days, up to 10 days, 15, 30. We'll make people's highest level of education into a number, basically years of schooling, so a high school diploma is 12, a bachelor's degree is 16, etc. Now you might be asking, why? Why take one measure that's a number and group it up, but take another measure that's a group and make it into a number? Partly the answer is just as an exercise to show you how. You're welcome to experiment and see what would happen with other specifications. Typically, when statisticians estimate machine learning models, they're going to normalize all the data, and so that's the first piece here. Create a new function, normvarb. This function takes in x in, subtracts the minimum, divides by the difference between the max and the min. So every normalized variable will be between 0 and 1 inclusive. In this case, I'm trying to classify decisions about mental health days, so I ask what variables are relevant in classifying. I'll start with people's education and age, along with ACE touch and ACE hurt. Recoded. I'll come back to that. I'm deliberately taking only a few classification variables because one of the other issues of geometric nearness is as we get into higher dimensions, it gets tougher to find neighbors in a sensible way. Our human intuition does pretty well in three-dimensional space, can understand forward, back, left, right, up, down. But what does five-dimensional space look like? I don't know. My poor human brain doesn't no capacity to visualize that. Most humans, that's true. One of the ways our human intuition can lead us astray is we have some sense of nearness in low dimensions, but that totally crashes in higher dimensions. So generally speaking, KNN estimators are not going to work very well if we add in too many different factors. But again, you can play around with yourself just to see. So to get back to the recode of ACE touch and ACE hurt, I've squished them to the 0-1 interval with a giant assumption that an answer of more than once gets a number 1, answer of once is a half. Never is 0. Is that a good assumption? No. But is it a usable assumption? We'll see. Again, you can try something else. Put these into a data frame, pick only the complete cases because this particular algorithm will choke if it has missing values. This shows you for x1 to x4, you can see a pattern to add x5 or 6 or whatever. Now in most machine learning, we split the data into training and test sets. Use the training data to train the model to do the categorization, then see how it does on the test set, which hadn't been used for the training, so it's new to the algorithm. If we want to train some algo to pick out cat pictures, we'd show it a lot of pictures and tell it this is cat, this is not cat. That's the training set. But we'd hold back some pictures that it hadn't seen yet, the test set, to ask cat or no, to figure it out how well it could do the categorization. Sorry. In this case, we randomly chose 60% of the observations to be the training set and 40% to be the test set. So the next line of code is set seed 1, 2, 3, 4. The hell is that doing? Well, we'll come on this regularly. The way computers work is if you tell it to pick a random number, computer's not actually going to pick a random number. Computers follow rules. It's going to pick what's called a pseudo-random number. A number that looks like it could be random, but is actually determined by a rule. In computer science, people have spent a huge amount of time worrying about this. It was a major innovation to figure it out. If you want to read some of the background help files about the details of the pseudo-random algorithm the computer is using, go ahead. It's kind of lovely. But all you really need to know for now is that the pseudo-random procedure takes a seed value and uses some algorithm to create a pseudo-random number. If we give it the same seed, then it will always pick the same random number. Maybe don't call them random. They're actually pseudo-random. Could call them good enough random numbers. Setting the seed, if I run the exact same estimation again, I will get the same random numbers chosen. Which is actually helpful in making your code so that somebody else can run it and get the same results. If you run this on Friday, somebody in your study group does it on Saturday, you'll get the same numbers. Anyway, That seed value of the next line code selects 60% of the sample at random, pseudo-random. The UNIF is picking these random numbers from a uniform distribution between 0 and 1. It's going to be a whole long list. If the random number is less than 0.6, it returns a value of true. If it's greater than 0.6, it returns a value of false. That's just a way of randomly splitting the data, so 60% goes in the training set and 40% goes in the test set. Then the lines give a summary of the data we're using, mostly so you can check that it looks okay. Where not okay would be if there are lots of missing observations or the numbers are not between 0 and 1 like we thought we told it to do. Then there's the actual meat of the KNN estimation. I put inside a loop where the loop fixes the number of neighbors to be used, from 1 neighbor to 3 to 5 up to 9. Odd numbers, so there's never a tie vote. Each time it produces a set of estimates, and each time checks how well those estimates did in predicting the new data, the test set. How often does it get the right prediction? In the lab and class, you can mess around and try to do better, improve this simple model.